We are pleased to have our speaker, Brian Saunders, um, and he'll be speaking on the vital role of the oceans in climate change. Brian has a BS in biology and a MS in marine estuarine sciences at Western Washington. I can't even say estuarine, and he has a master's in it. And he teaches at where do you teach? North Seattle College, right?
I teach both at Shoreline College and the North Seattle College.
Yeah, there you go. So we have a number of his students here today. I have seen this presentation, or at least when they did similar, so I know it's really good. And I'm looking forward to seeing it again. Brian has requested to hold questions toward the end, but feel free to put them in the chat and I'll keep track of them and make sure they do get answered at the end. And if you have anything urgent, wave your hand or put something in chat that, and I will interrupt as needed, but we'll let him talk through and then there'll be plenty of time for questions at the end. So without further ado, I'm going to turn it over to Brian. Take it away.
Let's share my.
And I will, by the way, keep everyone else muted as much as possible, including myself.
All right. Can everybody see the screen all right? Has everybody got a nice view of that? And hopefully my sound is my sound is good.
Yeah.
So thank you, Ken, for the invitation. It's always nice to get invited to these things because I just enjoy the topic so much, and I have been teaching now for it's 25 years, and I've been teaching environmental science, the main biology classes, the majors and non-majors as well. And every now and then I get to teach the courses that I truly love, which are oceanography and marine biology, which I'm actually doing this quarter. And I'm not a climatologist, but I can. One of the things I've really been blessed with is the idea that I've got all these disciplines that I teach, and I found the synergism and the ability to cross-discipline a lot of these things. It gives me a little bit of a different perspective. And so with my oceanography teaching and my teaching of environmental science, I've really been had some right insight into how to present these things in a way that hopefully are not overwhelming. I know this group is actually pretty sophisticated. I think Ken has talked about the wide range of speakers you've had. So so hopefully everybody has already got a little bit of a biology and chemistry knowledge, and so I can kind of play on that as we go through. And as I said, I'm not a climatologist, but this guy is, Wally Brocker, who I love this quote from him back in the 1970s and 80s. He's actually one that many people say is the first person who coined the phrase global warming, although he kind of denies that. But the climate system is an angry beast and we are poking it with sticks, is one of his famous statements. And when I first saw that statement way back when, I kind of thought, oh, he's talking about Gaia and the Gaia hypothesis of Earth being this central organism and it's the angry beast. But the more I came into my studies and the more I began teaching the topic, I think Wally was talking about the oceans. To me, the oceans are the main thermostat of our planet, and it drives much of our understanding of climate. Anybody who recognizes the wonderful area we live in, the Pacific Northwest, and the incredible temperate climate we have, recognizes the power of the oceans and what they can do. So it's really something that became a little bit more focused for me as I went through my years of teaching. And of course, we have to at least acknowledge the idea of what's happening today with climate change. Climate change, of course, is a global phenomena that's happening as we warm our planet. And of course, the main culprit for the warming of our planet is the burning of fossil fuels. And I always challenge my students at the beginning of my environmental science classes. I always say, write me a more ridiculous, fictitious novel an advanced, sophisticated society that can travel around their globe in one day and send incredible spaceships out into to explore the universe, can communicate through devices and have medicines that can be incredible. And yet this sophisticated society still powers the main industry on the ancient remains of 300 million-year-old organisms. I mean, you just have to see these things to recognize how crazy this whole system that we've set up is. And obviously, it's a non-renewable resource. It's an unsustainable resource because we'd have to wait 300 million years to reestablish or put them back into their natural place. And I've often thought about how this little diatom, maybe living 300 million years ago, floating around the oceans, once viewed what it would be like in the future. And basically its carbon remains sank to the bottom. It got buried in a way that it became entombed and essentially mineralized into a hydrocarbon that we now pump out of the ground and refine it to put into our cars, our gasoline cars, so we can go get a carton of milk at the grocery store. I mean, it's just unbelievable that that's how this society is really made. And it's an amazing tale to really think about. And it's really created, and then to top it all off, the burning of these organisms, these ancient remains of these organisms, is now creating a huge problem. And it's a huge problem that is hard for people to grasp. It really is something that I find is the biggest and most dangerous environmental problem because of that intangibility that most people just can't feel or touch it. And I enjoyed the smell talk too, about how that's another perception that we're very good at noticing, but climate change, not so much. The actual story of oil is kind of fun. I recently read an article called "Addicted to Oil." It's a New York Times editorial article that was written last year, and it really talked about how oil has sort of been used or discovered over the past 200 years, and what it was originally started to be used for. And in many ways, we can't really think about life today without oil, because think about all the products that we have in our home that are absolutely dependent upon the oil products. The lacquer on your coffee mug, the stain and preservatives on your wood floors. These are all oil derivatives. So we are definitely hooked on oil. We are definitely addicted to this stuff. Edwin Drake, of course, was the first one to set up an oil field, I believe in Pennsylvania. But it's funny to think about how oil and even before those days, oil was a nuisance. It would get in the ways of the mining machinery. It would clog up and gum up machines and keep them from mining coal and all those things that they were trying to get at. It was really Edwin Drake who thought that we could use this product to actually make a serious economic gain from it. And he was the first to actually use it for making kerosene, which was used, of course, to burn oil lamps, and actually may have saved the whales, by the way, because whale oil was the main product being used to light our lanterns. And whales, of course, were going extinct all over the planet because of the over harvesting. So oil may have inadvertently saved them from going extinct, because it made it easier to make oil lamps out of kerosene than anything else. But of course, he died. Edwin Drake, it's kind of funny. He died penniless, basically, because his product never really took off until after his death, and then of course we now know the rest of that story. And it's kind of funny that oil was actually used in some of the first ways that you can think of. Snake oil that was being sold in wagons as they went from town to town. There was actually a really good documentary about how crude oil was refined into the snake oil that they could sell. And I find it kind of ironic, because now 99% of our pharmaceuticals, the feedstocks and the reagents, are all dependent upon hydrocarbons from oil. So it's just a real interesting irony that's come sort of full turn in that story. And before I get into the ideas of climate and what's happening with the climate change today, it's really important for us to recognize the differences between these two terms because they do get mixed up all the time. Our politicians tend to mix them up on a daily basis. Of course, weather systems, weather is what's going on out there right now, right? Or I was talking to Ken earlier about how summer faked us out. Summer was going to be here and now it's gone and we're back to some cool spring weather here in the Pacific Northwest. But that's weather systems, right? And climate, of course, is the long-term changes that happen over decades to hundreds of years, to even thousands, tens of thousands. And we look at what's the general movement of the temperatures and climate regimes in those time periods. So it'd be a mistake for a politician to look out on a cold winter day and say, "Oh, what global warming? It's cold as it's too cold out there to be climate change." Just like we would be, silly enough to mix them up by saying, "Wow, it's incredibly hot this summer. This has got to be climate change," right? That's mixing up weather and climate, and we really have to kind of refrain from doing that. And so I'll try and refrain from doing that as much as possible as well. So as I mentioned, the burning of fossil fuels is really the main problem that has produced our climate shifts that we're seeing today. But it's not the only thing that's adding to our climate change. We have a bunch of different gases that we know as the greenhouse gases, and they all have different contributions from different areas, but definitely the burning of fossil fuels and especially the fuels we use for transportation are by far and away the greatest input. And the greenhouse effect, I should mention, by the way, is absolutely a necessary good thing for our planet. We need the greenhouse effect. We need to be able to trap heat that is coming from our sun, because without it, we would be an incredibly frigid, cold planet. We would be, I believe the average temperature on our planet would be like a -20, -30 degrees Celsius. It would be absolutely frigid without a greenhouse effect. And it's these greenhouse gases that work by not being absorbing solar energy as it comes into our atmosphere. We can kind of see from this picture, and don't worry about the numbers. The numbers get a little bit complicated, but the main idea is that you can see that as sunlight comes in, some of it gets absorbed, some of it gets reflected, some of it hits the surface and gets reflected, but a lot of it hits the surface and re-radiates back out into space as a sort of re-radiated heat. And as this heat leaves, some of it will leave directly, but some of it gets hit by the greenhouse gases. The greenhouse gases then hit those re-radiated heat and sends it back down to Earth, or keeps it essentially as a blanket that covers the atmosphere of our Earth. So that's where we get the warming from the greenhouse effect. And as one could probably tell, if we pump too many greenhouse gases into our atmosphere, we're going to get more and more heat that gets trapped and gets, basically adds to our blanket, our cushion. And the way that greenhouse gases work, by the way, it's really a fascinating thing to think about how a greenhouse gas absorbs radiation or the re-radiated heat. It actually begins by, you can see these yellow sort of squiggly lines are supposed to be the re-radiated heat, and you can see it hits a greenhouse gas like carbon dioxide. It gets them excited. It essentially, they absorb it and gets them excited, and some of it gets reflected out, some of it gets reflected back down. But that's the essential way that greenhouse gases are so effective. And actually, to tell you the truth, CO2 is not a great greenhouse gas. It's actually a very poor greenhouse gas, as we'll see. Methane and nitrous oxides are way more effective in being able to do that because of their molecular configuration. But that's sort of the idea. And so if we now look at this more as a sort of simulation model, you can see our sunlight coming through our atmosphere, hitting the surface of the Earth. That then, of course, some of it gets reflected, some of it gets warmed, and then sends that heat back out away into space, but some of it then hits these greenhouse gases, which are these little fireflies you see going around our atmosphere, and they get excited and they reflect that heat back down. So it acts very much like a greenhouse. Anybody who has a greenhouse knows that the way it works is that sunlight passes through your glass panels. It'll warm your potting bench. It'll warm your cement flooring of your greenhouse. And as the heat then tries to escape, it gets reflected back down by the glass panels. Hence, the name, the greenhouse effect, is a very appropriate one. Now, as I mentioned, CO2 is the one we're going to be spending most time talking about, but as I mentioned, it's a very weak greenhouse gas. Methane is about 30 times more effective in re-radiating heat back down to Earth. Nitrous oxide is somewhere around 300 times more effective, and fluorinated gases can be up to 1,000 to 10,000 times more effective. So why do climatologists and geologists really focus on carbon dioxide? Well, it's because it's the main greenhouse gas that is in our atmosphere. It's the main one that gets produced when we burn fossil fuels. As you can see, transportation and industry, electricity are all also contributors. But it's definitely the one that not only is the main one that we see today, but when we look at the past, and I'll show you some graphs of CO2 ranges in the past, it's the one that seems to align the most with what happens with the climate of our Earth. So that's why biologists and, well, not biologists, but climatologists really follow carbon dioxide and use that as a measuring stick for how it is part of our climate system. Now, as a biologist, I can tell you that there's also another wonderful way that we can think about CO2, because it's not only tied up within the physical processes of our planet, but it's heavily tied up in our biological processes. So actually, from a biology perspective, we can think about CO2 in a very different way. And here's the wonderful formula that may have sent you screaming into the night if you were a biology student and don't want to remember your biology. This is the formula of photosynthesis, where carbon dioxide and water are essentially used by plants, taken up by plants, and then converted into a molecule that they can use for energy, for food. Basically, a sugar molecule here, C6H12O6, is the glucose formula, but they can make a whole bunch of different organic molecules with it. And they also release oxygen. And you can see that that oxygen then becomes the fuel source for us to burn those sugar molecules. As this giraffe is doing with the plant here, it's taking those wonderful starches that the plant has made, and as it digests it, it burns it with oxygen. And as it burns it oxygen, it basically makes energy for the animal, which then releases the waste products as carbon dioxide. So you can see it's a wonderful little cycle between the primary producers of our planet and the primary consumers, and so forth, and on up the trophic system. So that's why CO2 becomes a really fascinating molecule to think about, because it's involved in our greenhouse effect, and yet it's also heavily tied up into the biological systems of our planet. And as we watch the waning CO2 over climates past, we can see how life is also responding, not just because of the climate changes that occur, but because of the availability of CO2 to plants and oxygen to animals. Now, the story of CO2 is actually really fascinating, of how we started to study and really think about CO2 and its major role in the climate systems. It actually begins back in 1959. It's essentially a gentleman named Charles Keeling came from I think he came from MIT, where he actually developed the first machine that could measure atmospheric CO2. And he then went to Scripps Institute to take the measuring machine, and he took it all the way to Hawaii, where he went to the top of Mauna Loa, Mount Mauna Loa, just to build the Mauna Loa Observatory, where he could then start measuring CO2 in the atmosphere. And you might be thinking, well, that's an odd place to go and set up your machine, but it's actually a perfect place, mainly because there's no biological organisms that could live there. There's no plant life there that could interfere with his CO2 readings, and very little respiration that could also be involved in making his measurements skewed or somewhat slanted. So he set this up in 1958, and it was the first time that this is the first time we really started to measure CO2 readings. And the thinking of the time, late 1950s, they actually, most climatologists at that time were thinking that CO2 is pretty erratic. You're going to see a lot of erratic kind of behaviors because CO2 is just such a, it just had a lot of mystery to it for a lot of climatologists at the time. So when he set up his machine and he started to measure the CO2 in the atmosphere, initially what was essentially happening was that he started to see some kind of erratic patterns, and it kind of made him a little bit thinking, well, maybe those climatologists are right. It kind of goes up and down and up and down, and you can see all good projects start with some power failures. He had 2 power failures in his first year, but he quickly started to recognize as the year went on an amazing pattern, an amazing rhythm, where CO2 sort of peaked during the winter months and early spring, and then sank throughout most of the summer and most of the fall. This is according to the Northern Hemisphere, by the way. So we see in the late winter, early spring with the rising levels of CO2, and then the lowering in the summer and fall of the Northern Hemisphere. And this pattern sort of, now you recognize why it makes so much sense from a biological perspective, because what's happening is when you look at what's happening during the early winter, all the plants have lost their leaves and they've now decayed all of their plant life back into the earth, and it's decomposed, and all the CO2 has been released into the atmosphere. And then as early spring and summer kick in, plants come back to life and they suck up the CO2 during photosynthesis, and they remove it out of the atmosphere, put it into the biomass of their bodies. And that's why we get this dip that occurs during the late summer, early fall seasons. And when I first saw this pattern as a college student, it just stopped me in my tracks, because it's recognized that this is the planet breathing. The planet is actually breathing. It's inhaling and exhaling the CO2 rhythms of the winter and spring of the Northern Hemisphere. And Charles Keeling kept this machine going year after year after year, and we kept seeing this same pattern: an increase during one part of the year, a decrease in the next. But the pattern soon became a little bit more than just an up and down zigzag motion, as you can see from this graph. As we continue to measure from 1958, the overall pattern remains the same, sort of zigzag portion, but it kept rising and rising and rising over the years. And this became known as the Keeling curve. As you can see, it kind of curves upwards. And it was our first solid evidence that we are contributing this carbon dioxide gas from burning fossil fuels into our atmosphere. So it was the first time we could really have a definitive way of thinking about our effect on this planet. And of course, it's been used now. This Keeling curve is still being measured today, and it's being used now to really think about, well, how is this going to affect our future? If we keep going as business as usual, we could really do some crazy things with our parts per million. ppm, by the way, is parts per million of carbon dioxide. And we can also see what would happen if we were to suddenly curb our appetite for burning fossil fuels, staying around 420 parts per million. And so these numbers kind of jingled in my head. It started with about 310 parts per million, probably back in the 1800s. And we have now, the updated for 2021 here is that we now have about 410 parts per million. So we've added about 100 parts per million of carbon dioxide into the atmosphere for the last 150 years. Of course, by the burning of those fossil fuels. And we get up to 900, 1,000 parts per million if we keep going. That's by the end of this century. And that, of course, would be an amazing disaster, as I'll show you in just a bit. But what do these numbers mean? So I'm saying it jingled and jingled and jangled in my head about 410, 400. What does it all mean? What are these CO2 readings really, and how does it relate to the past too? Because that's really what we want to do too. We want to think about how the CO2 levels and the temperature readings relate to not just what's happening now, but what does it look like in the past, and how does it compare? Well, when we look in the past, and I'm not going to go through this slide very much because it's a lot of just a lot of information that I really don't want to spend time going through, but just I wanted to throw this out there just because, one of the things that I want to always make sure when I talk about climate change is that, science works in a way that of collaboration. We don't use one person's data or one person's idea, one person's, method for finding something out in how it's changed in the past. We use physical, chemical, biological data. And when we look at this, it's done by tens of thousands of scientists, all doing different methods. And then we sort of cross-triangulate what this all means as far as putting together CO2 levels in the past and temperature readings in the past. And as we can see, the overwhelming evidence shows that there's been some huge changes in CO2 and climate changes in the past. But we have seen that there is this incredible correlation between CO2 levels and our climate. And we have seen, what this might mean as far as temperature readings beyond, just 150 years ago. And then how that affected the life forms that lived during those times. So what does the CO2 levels, that 410 parts per million, mean for today? What does it mean for our temperature? Well, as you can see, since we started to measure temperatures using physical thermometers back in the 1850s, and we can see that the actual average temperature has gone up by about 1.2 degrees Celsius. So 1.2 degrees Celsius just doesn't seem like a lot. A lot of people look at me strange when I say, yeah, 1.2 degrees Celsius. And you can see, once again, it's not just one group doing this measurement. It's the European Union's doing this. China's got some labs doing this. And of course, the NOAA. And there's a whole bunch of groups, and they're all basically showing the same patterns. It's the way science works in collaboration with each other. So 1.2 degrees Celsius is what we've been increasing over the last 150 years. With about another 100 parts per million, about 410 parts per million. And you can see that if we could compare what that all means, what that 1.5 degrees Celsius means on a yearly basis. I kind of like this graph because it basically shows the abnormal abnormal from an average temperature. They take an average of what the temperature was like from 1850 to 1900s. And then the blue areas, that shows this by month. It's kind of like a pie chart by month. And it shows what years and what months were below average between that 1850 and 1900 average, or were above average, the red obviously being above averages and the blue being below averages. And you can really see a nice visual about what's happened especially over the last 50 or so years, when we've really started to see these unusually warm months and unusually warm temperatures as compared to those times in the past. It really becomes quite obvious to the eye. So let's look at this graph, which because we want to know what does it mean to be 410 parts per million? What does it mean to have an average temperature? The average temperature today is about 15 degrees Celsius. So where in the past has the temperature been about 15 degrees Celsius, and where in the past has our CO2 levels been at 410 parts per million? And I know this is kind of a cartoon graph, not a very scientific graph, but it does show about a million years in the past, the basic kind of construct of what the average surface temperature was on all those scientific data that I've been showing you about. Well, there's a couple of things before we get into those two moments in time. and what it means today, there's a couple of things that are very important to recognize. One is that you can see that climate change has occurred quite a bit in the past. We've had peaks of really warm periods, and this is just, of course, the last million years or so. And then we've had these troughs or these dips where it's been very cool. And it looks like it's been erratic, but we have to make sure that we understand that these are changes that are occurring over thousands to tens of thousands of years. They're not changes that are occurring over 150 years. That's incredible. We've never seen any moment in our past where we've increased by 1.2 degrees Celsius in 150 years. That just has never occurred. That is a unprecedented increase. The other thing that's really notable about this graph is that a difference between, let's look at this peak here let me just make sure I'm right. This peak here, which was about 14 degrees Celsius, and then a decrease of about 10 degrees Celsius. That change there, that 4 or 5 degree Celsius change, that's the difference between an interglacial warming period and a change. So you can see that small changes on this graph can have huge effects on the climate. So those are two things to take in on this graph before we even look at the past and those levels that I want to look at. So where has it been 15 degrees Celsius on average in the past? Well, we have to go back about 130,000 years when the temperature was, again, about 15 degrees Celsius. And when climatologists and paleobiologists look back at that 130,000 years ago, they want to look at, well, what was the Earth like when it was, again, 15 degrees Celsius? Well, one of the things that's incredibly striking about that time, all evidence points to the fact that sea levels were 20 to 30 feet higher during this 130,000 years ago than they are today. 100, again, we're talking about 20 to 30 feet. That's an incredible, huge difference in sea levels. And what about when was it 410 parts per million in the past? Well, we actually have to go beyond this graph to get back to a time in our past where we were 410 parts per million in carbon dioxide. We have to go 3 million years back. So way off of this graph. And what was the Earth like, according to the paleobiologists and the climatologists? What was the Earth like 3 million years ago? Well, the temperature was 3 or 4 degrees warmer on average than today, so about 18 degrees Celsius. And sea levels were anywhere from 80 to 120 feet higher than they were today. So that can stop anybody in their tracks pretty quickly, because that means, well, what is going, why are we different today? Is it because it's happening so rapidly? Is it because we're just not seeing the changes yet? And this is where we have to now bring the oceans into the picture, because as most oceanographers would tell you, right now we're being saved from those calamitous pasts of what they would look like by the oceans. The oceans are right now absorbing an incredible amount of the heat that is being produced by the greenhouse effect, that with these 410 parts per million. And it's taking a lot of that heat and it distributes it around the planet, and in particularly into the deep oceans. And I'll get to that in just a bit. But before I can go further into talking about what the oceans are doing with this heat that they're absorbing, and this graph, by the way, is in something, I think it's something like gigajoules of energy. I can't remember what it is. It's just crazy to think about how much heat is absorbed by the oceans. And so let me go ahead and talk quickly about how water can actually absorb heat. So I don't know if everybody remembers the wonderful chemistry of the water molecule. It's 3 simple atoms. It's the 2 hydrogens covalently bonded to an oxygen atom. And you can see that these lines here, these solid lines here, represent something called a covalent bond. And I hope your eyes aren't glazing over at this point in time, but a covalent bond is when, simply put, is when 2 atoms share electrons, and they're sharing these electrons. You can kind of think of these electrons as sort of buzzing around these hydrogens and oxygens, and hydrogen will bring an electron to share and oxygen will bring an electron to share. But the problem with the sharing between hydrogens and oxygens, it's not equal. And it's a very uneven type of sharing. The oxygen atom is what I call in my classes the electron bully. It's a very electronegative. It tends to pull electrons very closely to it. And so the hydrogen brings its electron to share, but the electrons are spending way more time around the oxygen than they do around the hydrogen. It's still sharing, but it's an unequal sharing. And you might also remember from your chemistry days that electrons are negatively charged. So if electron that was brought by a hydrogen is spending more time around the oxygen, then that means that oxygen end is going to be a slightly negative charge, not fully one charge, but a slightly negative charge. And because that negative charge is no longer spending time around the hydrogens, then it, of course, will be slightly positive. And so that change in the polarity of the water, polar just means that two different charges on two sides of a molecule, it's really what makes water special. That's the reason why water is such an amazing, even though it's just these three simple atoms, it's such an amazing molecule, because a water molecule, like in my glass here, they're not just floating randomly in that glass. They're actually moving around very rapidly, but they tend to form these bonds between the neighboring water molecules because opposites attract, right? And the negative side of the oxygen is attracted to the positive side of the other water molecule, which is next to the hydrogen. And they tend to form these very weak bonds called hydrogen bonds. And the hydrogen bonds is really what gives water the special property of being able to absorb a lot of heat. So what happens is that these hydrogen bonds are really weak. So they'll make and break these bonds in milliseconds. But as soon as they break one of these hydrogen bonds, they'll reform another one with another neighboring water molecule. It just kind of goes on and on and on. And let me just show you a quick video that might help sort of visualize what's happening here. So this is just showing us our same water molecule here. It's kind of moving around as it is. And these are light beams. These are just the hydrogen bonds that it would form. And again, between the slightly positive side of a hydrogen molecule and the slightly negative side, it's always the same sort of pairing. And you put this into a large glass of water, and you can see that all of these water molecules are forming hydrogen bonds with each other. And these hydrogen bonds can essentially break and release heat. So this is why it takes a lot of heat to actually make a pot boil, is because as you apply heat on your gas stove or on your cooktop stove, you agitate the water molecules so they move around, but they'll release that heat as they break these hydrogen bonds and form new ones. So what you have to do, you have to keep adding more and more heat. And as you add more and more heat, you eventually agitate these water molecules so much that they eventually liberate off the surface and become a gas. And that takes a lot of energy. So that heat can be stored within these water molecules, forming these hydrogen bonds and forming and breaking these hydrogen bonds, that it can then take that heat and move it around our planet. So what parts of our ocean are absorbing the most of the heat? Well, it should make sense that most of the surface is where the heat is being absorbed. But it's amazing to think that the deep oceans are actually holding a lot of heat as well. And that has the testament to the fact that there's a connection between the surface waters and the deep waters. There has to be a connection. And so otherwise, how would the heat from the surface get to the deeper regions? And so that's where we really have to think about these vital roles that the oceans are playing, because they're taking a lot of the heat, the excess heat that we get at the surface, and it's somehow transporting it to the deep. And this is the system that connects the surface waters with the deep waters. This is known as the thermohaline circulation, mainly because it's driven by temperature and also by salinity. Haline is the salt content of the oceans. And it's also known as the meridional overturning circulation, or the OMC, and also the conveyor belt system, as I was taught it. And it's an amazing system that shows how surface currents sort of move within these gyres, these circular motions within the northern and southern hemispheres of the major oceans, at least. But then there's also this really interesting connection between the deep oceans that will then carry a lot of the heat that gets absorbed by the surface waters down into the deeper regions. Also, what you have to also be thinking about too is that these surface currents are not just absorbing heat, but at the surfaces where also the photosynthesis is taking place, all those phytoplankton that we talked about that end up becoming oil droplets in 300 million years or so. These guys are photosynthesizing, they're absorbing CO2 as they photosynthesize, and they release oxygen. And that vital absorbing of CO2 and releasing oxygen also gets carried down into the deep. So this system right here is really an amazing system. This is the angry beast that Wally Brocker was talking about. And I often think about how Charles Keeling sort of found the lungs of our planet with his CO2 measuring, as atmosphere CO2 measuring machine. Wally here was talking about the Earth's circulatory system, because it acts really much like a circulatory system of your blood as you carry oxygen and nutrients around your body and distribute it to areas that need it. So let's have a look at how this graph or how this simulation really demonstrates the thermohaline circulation. So here's our major surface currents. And of course, oh, I should tell you that we focus mainly on the Atlantic Ocean, because this is where the deep waters are formed. They're not really formed in the Pacific Ocean because the Pacific Ocean is just too vast, it's too diffuse. Whereas the Atlantic Ocean is fairly narrow, as you can see, in comparison to the Pacific. And the main two bodies of deep water that form in the North Atlantic, also known as the North Atlantic deep water, and in the Antarctic bottom water, which forms the densest oceans in our world because it's so cold and saline. So what happens is, as I continue the simulation, you see these surface waters, the Gulf Stream here, the fastest current in the ocean, picking up huge amounts of heat in the tropics. And as it moves it towards these northern regions, it cools, it distributes the heat. And again, here it is. As it cools, it gets more dense and it sinks. And this sinking then carries with it the carbon dioxide and the oxygen that was picked up by the photosynthetic processes at the surface and carries them down to the deep waters. And the deep waters here are amazing because they can trickle along the deep floor for thousands of years, anywhere from 500 to 1,000 years before they re-emerge back up to the surface. So it's kind of interesting from a paleo, or at least a climatologist view, because you can actually go down and sample these deep ocean waters that were at the surface 300 years ago, and you can see what was the climate like, what was the water surface like at that point in time, because much of it's unchanged from when it dived back down. So this is the circulatory system of our planet. And it's also the system that right now is mitigating climate change. It's mitigating the excess heat that we're producing. It's mitigating the CO2 that we're releasing. And it's storing it right now in the deep sea. And now, is this going to be going on forever? Let me go ahead and start this again, because there's something that is now becoming evident as we look and study these ocean currents. We're starting to see them slow down. And this is what is scaring a lot of biologist and oceanographer, because what happens now if we start making the Arctic region warmer? What happens if our polar regions become warmer and there's less difference in their ability to cool this water that gets transported from the tropics to the northern regions? You can imagine what's going to happen is that there's going to be less sinking as the difference between the polar regions and the tropics start to become more even. There's going to be less sinking, less taking down of the CO2 and storing it, less amounts of oxygen being distributed to the deep oceans. And essentially what we can envision happening is ocean systems starting to die because the circulatory pattern is not being sufficient enough to supply the deep sea with the things that it needs. And when I'm going to talk a little bit about the most incredible past that we had, during which the ocean currents basically completely stopped and the deep sea died. And as the deep sea dies, you get these dead zones that develop, these areas where there's no oxygen at all. And it basically compounds the ability to absorb the heat, and it compounds the ability to absorb CO2. As the ocean's currents slow down, we're not going to be absorbing CO2 as much. And a lot of that CO2 is then going to be released back out into our atmosphere, adding to our greenhouse effect. So this is where we really need to start thinking about how we're going to deal with this from here on out, and how intently we're going to study the oceans. So it's not just that the oceans are going to help us forever. We know that these ocean currents are slowing down. And if they really slow down, then we're going to really see sort of this feedback loop of increasing the amount of CO2 in our atmosphere, less CO2 being absorbed by the oceans. And we can already see some of the consequences in climate change going on today. So what are some of these consequences? Well, we've all seen rising sea levels. And I believe this is this graph here shows the average of sea level from 1993 to 2008. And then again, using past data and future, or the data we've just recently learned, and how it affects the sea levels. You can see that for the last, I would say 50 years, we've had an above average increase in our sea levels. In fact, I think the last estimate I saw was that we are losing an acre of swampland in Louisiana per day or something like that. It's just unbelievable how much a little bit of rising sea levels is causing damage. We're gaining about 3.6 millimeters per year. This is sort of in the last averages from the last couple decade or so. Although last year we increased by 4.2 millimeters, and it doesn't seem like that much, right? A little millimeter doesn't seem like a lot, but that's the entire world, right? That's the average over the entire world, which is an incredible volume of water when you think about it. And when you think a lot of these island nations are barely a meter above sea level, even small changes can be disastrous. We're already seeing changes in our precipitation and our wildlife distributions. The last estimate I saw is that land animals and plants are moving towards the polar regions at 1.7 kilometers per year. Again, doesn't seem like a lot, but over a long period of time, that's a major shift in the way that animals are distributed around our planet. And marine life, they're moving it towards the polar regions at 7.2 kilometers per year. And this, by the way, is one of the reasons why a lot of biologists are looking towards these high altitude community systems, these ecosystems, because they've got nowhere to go but up, right? And there's only a limit of how far they can go up before they go extinct. So that's probably where we'll see our first major extinctions occur, is in these high altitude communities, because there's nowhere to go. And when we think about these animals moving in their migratory pattern, it's not like it's, a herd of elephants suddenly moving more towards an polar region. We're seeing these patterns all over the globe. And unfortunately, the animals that are going to be doing the best are those that can constantly move and adapt, and which are usually the generalist kind of species. Your rats and your cockroaches will do very well. Things like panda bears and other kinds of things that are very specialist are not going to do well at all. Agriculture is obviously changing. Some areas that we used to call the bread baskets are no longer bread baskets. They're now too dry and not enough, or too hot to actually grow crops. So we're going to see different areas open up, but not many countries are going to be big enough like the US that can open up new cropland areas and continue to grow and feed their people. Some areas are going to become extended in their growing seasons. But again, that kind of distribution won't be available to everybody in that system. And tropical storms are becoming an interesting topic. We are actually seeing an increase in the frequency and intensity of storms, especially in the Atlantic. This is kind of an interesting graph I got off of NASA, and I'll run it a couple times just to kind of explain it. It shows the paths of hurricanes. Green are just tropical storms. Yellow are tropical storms that hit land. And red are the tropical storms that are class 3 or above that hit land. And you can see that it basically shows us that the number of tropical storms over the last 50 years have definitely increased. And especially if you look at, we're coming up on 2005, which is most notable for Katrina, we can see that we get hammered on the southern coast by all these tropical storms. And then we kind of went through an interesting quiet period. There was actually between 2006 and 2012 or 2014, I don't think there were any major class 3 or class 4. So hurricanes and hurricane intensity isn't as straightforward as a lot of people think it is. And if you were to graph that out over, these are just the total number of tropical storms that have occurred over the last 150 years. You can see that there is, even though it's a fairly weak regression line, you can definitely see that there is an increase that's been happening. We've gone from somewhere around averages of 10 tropical storms per year to somewhere on the order of about 18 to 20 tropical storms per year. And not only that, but tropical storms are now becoming earlier in the season, and they'll extend later in the season. And that's obviously something that is very new and incredibly damaging as far as our economy goes. It should make sense why tropical storms are increasing their frequency and intensity, because they're basically fueled by warm ocean surface currents. Warm ocean surface above 26 degrees Celsius is really the fuel that creates these incredible low pressure zones that causes air to rise very rapidly. And as it rises very rapidly, carrying with it moisture, that moisture then gets released, and that creates wind, and the wind continues to be picked up and increase its velocity as more and more heat rises off the oceans. So we're seeing ocean current or surface currents being warmer. You can imagine you're going to get more of these low pressure zones developing over time. It's interesting they did a survey last year about how many people think climate change is actually going to affect them. And I was shocked to see, well, maybe I shouldn't be shocked to see, but only 29% of people think that climate change is affecting them. Believe me, it's already affecting us. You may not know it, but financially, health-wise, and even now that we've been through COVID, we can get a little bit clearer picture of how disease-wise can also be a factor that we're going to have to start thinking more about. But financially, tropical storms, for instance, cause an average of about $41 billion per year. Well, who pays for that? Well, we all do. Insurance policies. Try and get fire insurance in some areas of California now. Try and get flood insurance in some areas of Louisiana. You can't. Electricity bills are going up, especially those that are powered by fossil fuels. Food is going to go up just because of the way that we're going to have to be changing our infrastructure on where we grow food and how much we grow food, where we grow, and what kinds of foods that we can actually grow. Health systems, we've seen the amount of asthma over the last decade has increased in young children by 50%. That could be some other reason, but it could also be air particles. There's a lot of good evidence that ozone being produced at the surface level by fossil fuel burning is creating a lot of respiratory problems. And heat strokes, more people die from heat strokes than they do from hypothermia every year, about 3 times more. And that actually shouldn't be too much of a shock. One of the things I forgot to point out about that graph that showed our CO2 levels in the past and the temperature readings in the past, humans have basically been on our planet for about 300 to maybe 500,000 years. So not even 500,000 years. We've got fossil records that kind of go back that far. Well, if you look through that period, that time period of human evolution, we basically grew up in a glaciation period. We were basically in ice ages. We're a cold adapted species. We do really well adapting to cold. We don't do well adapting to heat. And I think it's that kind of becomes evidence when you look at the number of people who die from heat stroke every year. And smoke, we can think about the incredible nature of smoke and the burning of forest fires. I don't know about you guys, but last year was really bad on my lung capacity, and that's going to become the new normal. They say they're already predicting that we're heading into the worst, maybe the worst fire season this summer because it's so dry in much of California already. And disease vectors, we're going to have maybe warmer winters throughout this region that we live in, the Pacific Northwest, and a lot of people might think that's a good thing. But that also means mosquitoes around around our year round. They won't die off. And when you have more mosquitoes, you're going to have different kinds of species moving into our area through the movement of these wildlife regions, and they're going to be carrying with them more diseases. So we can definitely look forward to that as something to really be wary of. And we can think about the past. When I think about the oceans, I mentioned to you the time when the ocean basically died. That was the Permian Triassic extinction. And it's an incredible lesson to look at. You can see from this quarry that they're digging out here, see this real black region up here. This is during the Permian extinction. Basically, the entire oceans died. I think somewhere on the order of 95% of all 95% of all marine life died. 75% of all terrestrial life died during this time. And it basically happened because of a massive global warming, a massive increase in temperature, average temperatures. Of course, they got up somewhere on the order of 9 degrees Fahrenheit, which is about 32 degrees Celsius on average. So we're a long ways from that, right? We're only 15 degrees Celsius on average today. But it did happen because of massive CO2 increases. The CO2 levels got up to about 1,000 parts per million. Remember that graph I showed you about what happens if we don't do anything, if we keep going business as usual, we'll get up to 1,000 parts per million. So that is going to have this incredible effect on our temperature ranges. And I don't think we want to see the oceans die because that would be our quick death. It was the death of these guys, the trilobites. The trilobites have an incredible history, by the way. They may be considered one of the most successful animals on this planet. They lived for about 200 million years. Again, we've only been on this planet for 500,000 years. And these guys survived incredible times, but they could not survive that extinction during the Permian age. I do have a case for optimism, by the way. In that case of optimism, I know I can really sound quite dour. The subject of climate change can be quite depressing, but I keep telling my students that there's so much things we can do. We can have these meetup groups. These are great. I love the way that technology has become a great teaching tool or a great way for us to connect with each other. Grassroots are always the beginning for changes that have occurred. We think about the Clean Water Act and the Clean Air Act, that all came from grassroots organizations. Education, my kids know more about climate change than I did when I was in college. They've been taught this from the very beginning. So it's really amazing to see how that type of momentum really will spur us forward. Renewable technology is becoming more cheap. It's becoming much cheaper. It's becoming more reliable. It's becoming more of a mainstay in our industries. So there's really some amazing things to look forward in that region as well. And world policy leaders are recognizing it. And you know what? They're recognizing the threat of climate change, and they're performing actions. But the comforting thing is that they're not performing actions from a moral standpoint. They're performing actions because they recognize there's an economic gain. They recognize that if we curve our fossil fuels, and if you become the next country that can develop this new renewable technology, you're going to be a leader in the economic race. So there's a lot of huge incentives for companies and or countries to move away from the fossil fuel craze. And finally, just to think, I don't know if anybody had seen I did a very similar talk on Earth Day this year, where we had a town hall meeting, and we had the youth organizations at Shorecrest High School join us, and they spoke out. And if you haven't seen Greta Thunberg's 2018 address to the United Nations, it's inspirational to see the young people getting so involved and angry as hell that we're messing with their future, and we're not thinking long term when we should be thinking more long term in their respects. So I do have a case for optimism. I really do, and I think we all should, but change needs to happen. All right, I think I'll stop it there. My voice is just about gone, so if anybody has
Thank
any
you.
questions.
Oh, that was great. I mean, just fabulous. We have one question up there at least, and then a couple of questions, and I have a question or two myself. So this is from Larry. For 800,000 years, there was a close correlation between temperature and CO2, but I have not found the reason why the temp increases preceded the CO2 increase by about 800 years. Why not the reverse? I think that's going to take some parsing. Larry, if you want to pipe up.
Okay, yes. It's that normally you think of CO2 as being something that increases the temperature. But for some reason, I have not found a reason for this. So here, I'll put myself on video. That it seems that in this particular case, the increase in temperature came slightly before the increase in CO2. And so some people have falsely assumed this statement means that CO2 does not cause temperature increase. That isn't true. I mean, CO2 is the reason.
Right.
I still have not found a reason why the heating seems to have somewhat preceded the CO2 increase. And I don't know if you have any.
There's a couple thoughts on that. I think I know which part of the graph you're talking about, Larry. First of all, we have to recognize that CO2 is not the only greenhouse gas. It is the major player, but there are many others that are played out and can also have effects. But there are also other ways that the climate can warm, mainly from, for instance, during the Permian extinction, there's really good evidence that the Siberian lava flows were occurring at that point in time, and they had massive flows all over the Siberian plateau. And that also released heat from the interior of the earth. So there's a lot of different ways that you can actually kind of project where CO2 is not the only player, but definitely it's the one that seems to be the most prolific over long periods of time, even though all these other ancillary players can kick in every now and then as well. At least that's the way I would approach that answer.
Okay. I also wanted to say something. That many people seem to believe that the major way that we address climate change is through sacrifice, limitations, doing without higher costs and so forth. And I believe that those things are important elements of it. But there are a number of things that we can do to address climate change that are so positive, so desirable, so economical, that even if climate change did not exist, we would want to do it. For example, one of the 4 or 5 most important things we can do is to replace fossil fuels in transportation with electric power. Now, I have a Tesla Model 3. It's not a pure electric car. I could not imagine going back to an old-fashioned, dirty, noisy, rough gas car that costs way more to operate, that is less safe, less convenient to use. So the solutions are actually, in many cases, much better than what we have now. So while certain amounts of sacrifice and higher cost will be a part of it, that's not the whole picture. There's some very pleasant things to look forward to.
Yeah, and Larry, you've just hit on that last note. I just talked about how I have great optimism for that same reason. You know, yeah, we can use a lot of these new developments that move away from fossil fuels, and people don't they're not going to want to go back. And there are now products and even for instance, growing your own food can be incredibly rewarding. I just find that there's a lot of room for optimism based on what you've just said, and I would agree with you.
Thanks. We have a question from Marcelo. So he's talking about CO2. Talking about CO2 increase causes. Is it true the statement that the major cause before fossil fuel consumption is actually caused by the food production system, which includes agriculture, food chain supply, and transportation? If that's true, before thinking about how to change transportation technology, shouldn't we first be thinking about how we eat, what to produce and where, and less waste and so on? So I guess this is kind of how serious is the agricultural piece of climate change or CO2 production,
It's huge.
or both?
It's huge, Marcelo. Absolutely. And that's where a lot of those other greenhouse gases come to play. Methane gas produced from essentially from the cows themselves are incredibly important in that. And then the use of machinery to do the transportation of foods. That's why I think when I said one of the most amazing things you can do to avert climate change is to start growing whatever food you can. Even if you have an apartment, a windowsill garden with lettuce, those kinds of small changes are huge. And I think that has that'll have a huge impact on the amount of fossil fuel burning for agriculture and the emissions that they produce.
And I have a specific little question. You talk about the flows deep within the ocean that can be 300 to 1,000 years old. How do you know how old that is? If you go down and sample some of that water, how do you know how old it is?
Yeah, I mean, there's again, not being technically gifted in that part of oceanography, but they can base it on, I believe, the isotopic ratios of certain gases, for instance, oxygen and CO2 and other kinds of molecules that they trace, and then based also on there's amazing things that they can actually tell. They can tell where that water particle came from based on some of the other kinds of isotopes that they measure. And just by looking at measuring the speed of how things move, they can kind of do these estimates of when that water might have been at the surface, kind of thing. Assuming again that it hasn't changed over that last 1,000 years as far as the circulation goes.
Yeah.
So
yeah, you have a chicken and egg problem there. What
yeah.
Which one? But I presume they know what they're talking about.
Yeah.
Okay, we have a question came in from Toby. I appreciate your slide regarding optimism. Besides what you just mentioned regarding diet, fossil fuels, etc., are there relatively accessible and practical suggestions you can recommend that we can incorporate into our lifestyles? I, for one, am big on electric cars. I have a Leaf myself. So.
Yeah. I have an electric car as well. But Toby, the number one thing I think you can do is just as a concerned citizen is to vote. Vote for people who believe in climate change. Vote for people that are going to make policies, and don't just vote for them. Make sure they follow up. Biden with his policy to cut emissions by 2030, I think he said by 50%. Let's make sure he does that. Let's not let him get off the hook. In fact, let's say we demand more. We want to see more reductions. So that is probably the most powerful thing I think a lot of people can do is just to really get out there and make some noise. As I said, if you haven't watched Greta Thunberg's talk, it's very inspirational to hear someone so young talk so eloquently and clearly.
So the big things are electric car,
Mhm.
food sources, and then basic things I'd assume like insulating your house properly.
Yeah.
I know here, or I understand here in the Northwest, most of our electricity is reasonably, well produced, hydropowered, so it's less important for us to have solar panels. Um, but are there other specific things? I love their comment about voting. I think that's great. I don't think that occurs to a lot of people.
Yeah.
Um,
No, I mean there's a huge handful of things that you can do, and Ken, you mentioned most of them, which is if you're a homeowner, then you make sure that you're well insulated, you're heating your home well, you're not using a lot of energy to heat up your house or cool it down. There's a lot of uh, simple things like that we can all do. Driving less, walking more, using public transportation, especially when the light rail gets put in. That's going to be an amazing game changer in my view, to be able to take that downtown rather than getting to my car, even though again I have an electric car, but getting into a car going into traffic is not fun. Yeah, there's a lot of ways that I think you can do that's not altering your lifestyle too much.
Yeah, Larry actually did a presentation a couple of 3 years ago now on how you can keep essentially the exact same lifestyle we have now and yet be far more efficient.
Yeah.
Maybe it'll be time to rerun that talk, Larry, in a few months or something,
Mhm.
because it is, um, we. I think a lot of people think that we have to sacrifice our lifestyle in order to save the planet. And maybe there are some things we do have to sacrifice, but there's an amazing amount you can do and still have the modern uh, lifestyle.
Yeah.
One of the important things that many people can do if you are changing your water heater is to get a heat pump
Yeah.
type water heater. It does
Agree.
cost about $800 more, but it drastically reduces the amount of energy needed. The uh, heating water is one of the biggest uses of energy in your house, and a heat pump water heater will cut that by about 2.5 times.
Yeah.
So that's a major thing that each individual can do.
I understand also if your refrigerator is more than 5 years old, it you'll pay for itself by getting a new one because they're so well insulated now. We put a heat pump on our house, and I'll certainly when we replace our water heater, I'll do a heat pump for that. And we saw our electric bill drop by 30 to 40% instantly. So
Yeah.
if you have electric heat, by all means, you want a heat pump because we're the perfect climate for it. At that point, are there any other questions for Brian? Now's your chance. Speak up or type them in chat. Otherwise, we're gonna wrap it up here. I'll put in the plug for August for Aretha Weeks talking about the sense of smell. I think she has a lot of interesting insights on that. She offered a couple of interesting topics. I had to flip a coin, and that one came up ahead. So I'm hoping to tap her for some other stuff too, but I think this is going to be a fun talk. So thank you all. Again, a lot of people here for the first time, and I appreciate that. I hope you enjoyed it. I will be posting a video of this as soon as it's ready. Like I say, it usually takes a few days to get it uploaded and a little bit of editing. So keep an eye out on the meetup.com page for that. So, oh, hang on. We do have a question here. This is Nancy, in the 70s, we talked about zero population growth. What are your thoughts on population? I'm glad she brought that up because I was also thinking one of the best things you can do is one fewer kid. Do you have any comments on that? This might be controversial, so feel free to.
Yeah, that's a fairly but I don't mind saying, one of the things that is fairly self-evident is that population growth, for humans in general, is actually slowing. It's still growing exponentially, but I think that becomes, to me, it becomes more again a factor of how that person lives their life, and that's something that we're seeing quite a bit. Especially here in the developed countries versus developing countries, it's something that we all need to kind of think about on a personal basis. But I can see population not being as huge a problem in the averting climate change as technology can be, and just from people, being able to change their energy uses.
If I
That
could say something here, that one of the things that China did that was bad is a prescription or proscription on how many kids you can have. That's not the way to do it.
Yeah,
It
definitely.
turns out that the best way that you can do to reduce population growth is to educate women. If you make life good for women and well, for everyone in general, but for women in particular, that has the biggest effect on on stabilizing the population. There's um, probably it's one of the two or three most important things that we can do.
Yeah,
Right there, yeah.
yeah.
But
Empowering women. It's definitely a big way to add to that. Yeah.
we have another question that came in. How do we get through to people who do not think climate change is happening or do not feel personally effective? How can we make the big change needed when there's so much distrust of science and misinformation out there? Oh, that's a good one.
Yeah, that is a good one. And there are some people that you just can't convince. And that's, what I for people that are um usually people when they come to me and they say, I don't believe in this, whatever, because this is the information I got. I always like to say, well, show me your information, show me where you're getting your information from, who's your sources. And so one of the things, if you have just a real, educational discussion with somebody, usually you can figure out that it's the sources that are the problem. And that's we're all flooded with these information. We're all flooded with things that we have to sort of sort through and pick through and make sure that we are seeing the data as it is. But the mistrust of science to me is something that has always been a kind of a conundrum, because we trust science in so many other ways, but as soon as it becomes something that is inconvenient for us, we tend to distrust it. So it's something, again, that I feel like, just provide people with as much information as they possibly can, and let them make their own decisions, but you can't really force them in that.
One of the techniques that I use is people. There's the parable of the blind man and the elephant, and one of the uh, reasons people give for distrusting science is they say, "Well, back so many years ago, they said such and such, and that turned out not to be true." And the reason is, if you look at the blind man and the elephant, the way it goes is that one blind man grabs the tail and says, "An elephant is like a rope." Another grabs a leg and says, "An elephant is like a tree trunk." Another one grabs a tusk and says, "An elephant is like a stone." Now, they're not lying. They're actually observing things correctly. And if they walk away and don't talk with one another, there'll be no reason to change. But if they start talking with one another, and in particular, if a large number of blind men examine a large number of parts of the elephant and all communicate, they will eventually come up with a true solution of what the elephant is like. That's what happened with climate change when it's a complex situation. You
Mhm.
have people who have uh, actually discovered real things. They only operate within their particular area. And some would say, well, the climate is cooling because of this. Another would say climate is cooling because of that. Another would say climate is increasing. It's only when all of these views get together and there's a large communication over a period of time that these things get resolved.
Yeah, and that's an excellent point about how I pointed out that, that we're not basing this off of one person's opinion. This is based off of a collection of thousands of scientists. And the idea also that Larry brought up is science is not a perfect thing. It doesn't always, we don't always see exactly at that time what the truth is. science doesn't prove anything outright, right? It only provides evidence for things, and we can amass that evidence and make some decisions based on the best available science. It's constantly evolving, it's constantly changing, and so we have to constantly be adjusting of what we think is the truth based on what new evidence comes up.
All right. Okay. Unless there are any last questions, I want to thank you all for attending. Brian, thank you very much. That was great.
Oh yeah, absolutely. Thank
And,
you for inviting me.
Again, thank you all. Keep an eye out on meetup.com for future talks, and have a great summer, everybody.